equilibrium, we'll be studying about reversible reactions and equilibria reactions, a chemical equilibrium, and also the factors which affects the equilibrium. I would say most of it, like 90% of this chapter, is what you have studied for O levels. Nothing, only Le-Chatelier's principle is introduced. The rest of it is all what you have done before. So let me first introduce you what is a reversible reaction is and difference between reversible and equilibria reaction. Now, a reversible reaction is a reaction where reactants react together to form the products, and products react back and form the reactants again. To represent this type of reversible reactions, we use this reversible arrow. These are the reversible arrows, right? And never use this type of arrows like double-headed arrows. This is not, it doesn't represent reversible reactions. In fact, this type of double-headed arrows we use in A2 to show resonance structures or canonical structures. That is done in A2. So never use double-headed arrows to show a reversible reaction because it has a different meaning, right? So a reversible reaction is a reaction where reactants react to form the products, and products react back to form the reactants under the same conditions of temperature, pressure, and concentration. Now, these conditions of temperature, pressure, and concentration are referred to as macroscopic properties, right? There are so many examples for reversible reactions. Let me write a few examples here. Nitrogen gas reacting with hydrogen to form ammonia is exothermic. It's a reversible reaction. It's exothermic reversible reaction. Sulfur dioxide reacting with oxygen to form sulfur trioxide. Dinitrogen tetroxide decompose into give nitrogen dioxide. These are examples for reversible reactions, right? So any reaction, will be reversible in a closed system, right? It's always better to have a closed system because open system will allow the matter to enter or to escape, right? Yes, we can copy these three examples. Right. So what's the difference between reversible reaction and equilibria reaction? What happens in chemical equilibrium? Now, in chemical equilibrium, it's a state of balance, right, in which the rate of the forward and the backward reactions, the rates are equal. So what happens in equilibrium is that initially, the concentration of the reactants are maximum, right? Any reaction, at the initial stages, you have the maximum concentration. Say, for example, I'm mixing A and B together. The concentration of A and B is maximum at the initial stages. So what happens? The frequency of the collisions also will be maximum at the initial stage. That results in faster reaction rate. So in any reaction, the initial rate of the reaction is maximum. That's we discussed kinetics before. And I drew the red graph, and you can prove it from this. You can see the gradient is maximum initially. Initial gradient is the initial rate. Then, at time t, you want to find the gradient, that will be less than the initial gradient. Eventually, gradient becomes 0, right? So in any reaction, the initial stage is the fastest because concentration of the reactants are maximum. Because collision frequency is high. So as it forms the products in a closed system, the backward reaction is 0. But when there's a significant amount of products produced, then the products C and D will begin to react and slowly start the backward reaction. But the thing is, the rate of the backward reaction at the initial stages will be the lowest. It will show the lowest rate. Right? Forward reaction, initially, it will show the highest rate, because the concentration of the reactants are maximum at the initial stages. With time, concentration gradually decreases as more and more products are produced. The backward reaction will begin, but the rate of the backward reaction will be minimum at the initial stages. But no sooner, when more A and B reacts to form C and D, the rate of the forward reaction will gradually decrease. The forward reaction rate will gradually decrease. Right? And when there are more products produced, the backward reaction rate will increase gradually. The backward reaction rate will increase as more and more products are produced, because as the concentration increases, rate increases. There will come a point where the rate of the forward reaction equals rate of the backward reaction. That is, initially, the forward reaction rate is maximum, with time is dropping, decreasing. Backward reaction rate is minimum initially, start increasing. There will come a point where the rates of both the forward and the backward reactions become equal. And that is the point where we say the system reaches equilibrium. It's a state of balance where the rate of the forward reaction equals that of the backward reaction at constant macroscopic properties. What I mean by macroscopic properties is that the temperature, pressure, and concentration. Why these three? Because these three are the factors which affects the equilibrium, position of the equilibrium. That means when a system reaches equilibrium, there's a specific temperature, a specific pressure, and concentration of the reactants and the products to maintain the equilibrium system. If you do a change in the temperature, pressure, or concentration, what happens? The system will come out of equilibrium. What I mean by coming out of equilibrium is that it might either favor reactants or it might favor the products. Got it? So remember, not all reversible reactions reach equilibrium, but all equilibrium reactions are reversible reactions. I repeat again, not all reversible reactions are equilibrium, but all equilibrium reactions are reversible. Good example for a reversible process which is not equilibrium is that the heating of hydrous copper sulfate. The hydrous copper sulfate is a blue solid. When you heat, it turns to anhydrous copper sulfate. It loses its water of crystallization and forms the anhydrous copper sulfate. No sooner when you cool the anhydrous copper sulfate, it absorbs the water of crystallization and forms the hydrous blue copper sulfate. So these are also a reversible process. But it will never reach equilibrium, because to favor the forward, you have to heat, favor the backward, you have to cool. They have to change the conditions. If you want to form the products, you have to heat, form the reactants, you have to cool. But equilibrium is, chemical equilibrium is not like that. Under a set of conditions of temperature, pressure, and concentration, reactants actually react to form the products, and products react to form the reactants, and these two rates will be equal. When the rates are equal, we say the system reaches equilibrium, chemical equilibrium. Am I clear? So chemical equilibrium is a state of balance in which the rate of the forward reaction equals that of the backward reaction at constant temperature, pressure, and concentration. Particles of the reactants will be bombarding each other, and if they possess energy higher than the activation energy, the effective collisions will result in the formation of products. At the beginning, the rate of the forward reaction will be higher as there are more molecules resulting effective collisions. The rate of the backward reaction will be zero. As the products are formed, the rate of the backward reaction will gradually increase. A dynamic equilibrium will be achieved when both of these rates become equal in a sealed container. It's very important. It should be a closed vessel or a sealed container, because open system will allow matter to enter or to escape. That means for one of the products or the reactant, if it's a gas, open system will allow the gas to escape. Or sometimes then they may not be gases, but still, if it's open, air might react with one of the reactants or the products, and side reactions will result. So it has to be in a closed system. Now, chemical equilibria are referred to as dynamic equilibrium. There are two types of equilibria: static and dynamic, right? For example, now daily life, if you take static equilibrium, example of static equilibrium is that you take, say, a balance, right, and keep equal weights on both the sides, right? This is a state of balance, right? This is an example for static equilibrium. Dynamic equilibrium, say, for example, a child ascending the escalator at the same speed as the escalator descends. This is also state of balance. What happens to this child? He'll be in the same place, right? He's trying to go up the escalator, and that comes down the same speed. Speed is same. He'll be in the same place. But there's a difference between the two. In static, so I put 10 grams on each side. 10 grams is present as 10 grams. There's no change in the mass. So here, what happens? The child continuously doing some work in the opposite direction, right? So this is dynamic. That means all this change is taking place. All this work is done. So all chemical equilibria are dynamic, which means what? A and B reacts to form C and D. Always A and B keep reacting. Always C and D is reacting, because their rates are equal. The amount of reactants and the amount of products, the concentration of it will be constant. It may be equal, it may not be equal, but concentrations are always constant because rates are equal, right? So in chemical equilibrium, always a change is taking place. Reactants react to form the products, and products react to form the reactants, and the rates will be identical. Therefore, the amount of reactants and the amount of products will be always constant. It's not going to increase or decrease because rates are constant. There's a continuously change taking place, so you always see the reactants, and you also know always the products. The intensities, the concentrations will be constant, but continually change taking place. So dynamic means that the molecules or ions of reactants or products continuously reacting. It is a reaction which occurs in both directions, where rate of the forward reaction equals that of the backward reaction at constant macroscopic properties. Clear? So dynamic equilibrium, always it's dynamic meaning continuous change is taking place while reactants and products are continuously reacting, and rates are equal, and the concentrations of the products are and the reactants are constant. Concentrations don't change. It can be equal, it can be not equal, but the concentration amounts will be constant. This is also a common misunderstanding among many students. They think once system reaches equilibrium, the concentration should be equal. No, it's not a condition. It can be equal, it may not be equal. Yeah. So equilibrium always happens in a closed system because open system allows the matter to enter or to escape. Okay, so I will conclude with that for today. Next week we'll study how the temperature, pressure, and concentration affects the equilibrium, and the Le-Chatelier's principle and the details of it will be discussed in the next lesson. Any questions? There's a question. Yes, from the next question, question 6, right? Just remind me the question 6. We're starting from question 6 and completing the tune in the next lesson. Right? No questions, right? So no questions. I conclude for today. Hope you enjoyed the lesson. See you next week at the same time.
You are currently the only person in this conference.
Welcome back to the virtual classroom of Chem-based School of Chemistry. Can you hear me? Sound clear? Right. In the previous lesson, we started on equilibrium, chemical equilibrium. And I gave introduction to equilibrium, and I said I'll be completing the lesson today. So I think I did up to page 2, right? Page 2, question 6 or 7, if I'm not mistaken. Let me just brief you on the whole thing again quickly. We know what is reversible reaction and what's the difference between the reversible reaction and the equilibrium reaction. Reversible reactions, not all reversible reactions reaches equilibrium. A reaction will be reversible if the reactants give products and the products react back to form the reactants. But not all reversible reactions, they reach equilibrium. Equilibrium, as for the equilibrium, is a state of balance in which the rate of the forward reaction equals that of the backward reaction at constant temperature, pressure, and concentrations. So these factors of temperature, pressure, concentrations should be kept constant to maintain the system at equilibrium. Right? So when the reactants react, it forms the products. The rate of the forward reaction will be maximum at the initial stages because you have a lot of reactants. But the backward reaction will be minimum because initial stages only few products are produced. So as more and more reactants get used up to form more and more products, the rate of the forward reaction gradually decreases because the reactants decrease their concentration with time. As more and more products are produced, the backward reaction will begin. So the forward reaction rate is maximum and the backward reaction rate is minimum at the initial stage. So with time, the forward reaction rate will drop and the backward reaction rate will rise. And eventually, there will come a point where the rate of both the forward and the backward reactions become equal. That's the point where we say the system has reached equilibrium. In fact, all chemical equilibria are dynamic equilibrium. As I mentioned last week, there are two types of equilibrium, static equilibrium and dynamic equilibrium.